All right, welcome back to our next lesson. So we're going to be looking at calculating concentrations and equilibrium constant values using ICE tables. So we're going to get into what that actually means. So of course, when we're studying equilibrium systems, we do not assume quantitative reactions. So therefore, ICE tables are going to have to be used to find concentrations at substance at equilibrium. So what the ICE table stands for is that it is a table constructed indicating molar concentrations at the following points in time during a reaction. The initial, or the I, the change, so how the concentrations are changing as the reaction progresses, and of course then the equilibrium. So initial, change, and equilibrium stands for I.C.E. or our ICE tables. So the initial is the molar concentration at the start of the experiment. The change is the change in concentrations due to the stoichiometric coefficients. And of course, equilibrium is what we're left with when the reaction is done. So what we have is the initial concentrations are going to be stated in the question. So products have not formed yet, so the concentration is equal to 0 before the reaction starts unless otherwise stated. So please read carefully, because if it's saying that we inject a part of the product first, you are going to have to put that in, but we'll kind of cross that bridge when we get to it. Now, when we look at the C, the change, this is between the initial and equilibrium conditions. So the change represents the actual reaction occurring until equilibrium is established. Now, reactants are consumed stoichiometric per the balanced chemical equation. So that means if there's a big 2 in front of one of the reactants, that means 2 of those molecules need to react. So it changes the concentration based on that because 2 need to react. So similarly, the products are going to be formed stoichiometric per the balanced chemical equation as well. So that means if 3 moles are being produced, then, well, that's how many moles are being produced. So we are going to need to keep that in mind as we are writing in our ICE tables. Now, change for the reactants are going to be negative because they are used up, whereas the change for the products are going to be positive because they are being produced as the reaction progresses. Then, of course, equilibrium concentration. This is just going to be the concentrations at the end of the reaction. So what we're going to have to do is subtract the change. So when we calculate our change here from the reactants, we're going to have to add the change to the products. Now, when we do our first example, it'll make a lot more sense. So now, generally for questions, you're not going to be given an ICE table like this. Of course, for these here, I'm giving them to you just until you kind of get going. Now, when you're reading these questions right here, make sure to look for the words initially, because that's going to tell you what initially goes in, and then of course, and at equilibrium. Because then that's going to tell you what you put in for your equilibrium concentrations. And that's just because there's going to be a bunch of different concentrations getting tossed out there, so you don't want to get confused. So, in example 1, in the formation of FCl7, so this is a formation reaction, chlorine gas was initially, or 6 moles per liter of chlorine gas was initially mixed with 2 moles per liter of fluorine gas. At equilibrium, so notice here, initially at equilibrium, 1.5 moles of fluorine heptachloride was produced. What is the constant? So of course, first step, we need to write out our balanced chemical equation. So this is a formation reaction. And we need to balance, like so. So once we have our balanced chemical equation, now we can actually construct our ICE table. Now, like I said, these are normally not provided for you. You have to kind of draw these out. But we kind of take our reaction and put it here. Like this. Now, initial concentrations we're going to get from the question. So in the formation, 6 moles per liter of chlorine gas was initially mixed with 2 moles per liter of fluorine gas. So that means our 6.00 moles per liter was initially mixed with our 2.00, and that's it. Now, it says at equilibrium 1.5 moles of fluorine heptachloride was produced. Now, this is at equilibrium, that's down here. So initially, because we don't have anything, we're going to assume that 0 moles per liter of fluorine heptachloride is there because the reaction hasn't started yet. So at time 0, concentration of one of our products is 0. Now, how we figure out the change. This is why we need that balanced chemical equation, because how we read this is 7 moles of chlorine reacts with 1 mole of fluorine to produce 2 moles of fluorine heptachloride. So that means for one successful collision to take place, we need 7 chlorine molecules to react with 1 fluorine molecule. So that means that we are going to lose 7x of our chlorine. Now, the reason we're using X because it is an unknown amount that we're going to lose, but we know that 7 molecules need to react. Whereas our fluorine, we're only going to be losing 1. Now we're going to produce positive 2x, right? Because 2 molecules are produced for every 1 successful collision. So that's why these molar coefficients are so important, is that they're telling us how many we're actually gaining or losing as the reaction progresses. So at equilibrium, our fluorine heptachloride, we're going to have an expression of 6.00 minus 7x. Our fluorine, we're going to have 2.00 minus x. And our fluorine, we're going to have 0 plus 2x, or just 2x. Now, from our question, we'll notice it says at equilibrium, 1.5 moles per liter of fluorine heptachloride was produced. So we're going to have 2 expressions. For fluorine heptachloride at equilibrium, which this is going to be very important because our next step, once we have all this, we're going to solve for x. Now, because fluorine heptachloride has 2 expressions, for equilibrium concentration, use that to solve for x. So that means we have concentration of FCl7 is equal to 2x, and concentration of FCl7 is equal to 1.50. So we are going to combine 2 of these equations together to get 2x is equal to 1.50. And of course, we divide both sides by 2, and x is equal to 0.70. Oh, 0.750, sorry. And that is our x. So what we can do now is go back and actually plug in all of our values up here, right? So that means concentration of Cl2 is 6.00 minus 7x. And when you plug all that in, you get 0.750. And concentration of fluorine was equal to 2.00 minus x. You plug that in, and we get 1.25. All right, so we have concentration at equilibrium, concentration at equilibrium, concentration at equilibrium. So now we can finally solve our equilibrium constant. And that is our last step. So our equilibrium constant is equal to concentration of FCl, so our product raised to its exponent over our products. So Cl2 is raised to the power of 7, and F2 isn't raised to the power of anything. So we put in our equilibrium concentrations. And when we evaluate, we get a number of 13.5, which says products are favored. And that is how we can use our ICE tables to now evaluate equilibrium constants and kind of figure out some more complex reactions. So a lot of these are going to be very similar, where we're given enough information inside of the question, and it just comes down to when you do get to this point, when you fill out all your equilibrium stuff, you follow this rule every single time. Try to find that one expression that has, or that one compound that has two expressions for equilibrium concentration, so you can solve for X. So example 2, I don't know why there was a blank page there. So example 2, we have a new system, so hydrogen plus bromine produces 2 HBr. Now initially 8 moles and 8 moles was placed in 2 liters. So our first thing in this right here, where we're not concentrations, you do need to solve for concentrations first. I'm just doing this really quick. And you can do the same thing for bromine as well. All right. So this is initially, we're placing it here. So when equilibrium is established, so this is kind of the cutoff where we have our initial things right here. So if we have H2, Br2, and 2 HBr, initially we know was 4.00 and 4.00 and 0 for HBr, right? Because it says when equilibrium was established. So that means, you know, equilibrium. So we're done with our initial stuff. So we can write in our change, minus x, and plus 2x. So remember, reactants are used up, so that's why it's minus x. Molar coefficient is 1, so that's why there's nothing in front of those x's. Whereas for our HBr, there's a coefficient of 2, so we're going to get plus 2x. So we're going to get 4.00 minus x, 4.00 minus x, and 2x. Now, as we read, when equilibrium is established, the molar concentration of bromine in the mixture was 1.46. So we will notice that for this particular one now, bromine has 2 expressions. So we're going to have to use this to solve for X now, where we have concentration of bromine is equal to 4.00 minus X, and concentration of bromine, Br2, is equal to 1.46. So we're going to combine two of these expressions. 4.00 minus X is equal to 1.46. And when we just kind of solve, X is equal to 4.00 minus 1.46, and X is equal to 2.54. All right. So we can then use that and solve for our other equilibrium concentrations, which we just said, well, concentration Br2 is equal to 1.46. Concentration of H2 is equal to 4.00 minus X. That equals 4.00 minus 2.54. That is equal to 1.46. So we have hydrogen and bromine. And of course, concentration of HBr is equal to 2x. And that is equal to 2 times our x value. So just be very careful when you're dealing with these here. 2.54. And we get a value of 5.08. So from here, now we can write out our equilibrium expression, which once you get that, it's going to look like this. And it's going to look like that. So we have HBr squared over H2 and Br2, and when we evaluate everything, we should get 12.1, which is indicating that the products are being favored. So that is kind of a lot of the equilibrium stuff is going to look like that. It's where you're given enough information, and of course you do need to just be careful on how you evaluate X and everything like that. So example 3, you will notice initially 12 moles of hydrogen, 12 moles of bromine, and 12 moles of hydrogen bromide gas are placed in a 1.5 liter container. So notice that this one here, we have a concentration of one of our products being initially injected in there as well. But really, it shouldn't change the value of the equilibrium constant that much with rounding and everything like that. We might get a little bit of a different answer with rounding, but that's no big deal. But also, we don't know what temperature this is at either. All right. So at equilibrium, the molar concentration of hydrogen bromide gas in mixture was 15.2 moles per liter. Predict the equilibrium concentrations for the equilibrium mixture and calculate Kc. All right. So of course with this one here, it's the exact same reaction as the previous one where we got H2 plus Br2 is equal to 2 HBr. So this one right here, pause the video and see if you can solve this one on your own. And the answer is going to go up in about 3 seconds. So pause now. All right, and your answer should look something like this. So we have our reaction here. Now this type right here, we will notice that because one of the products was initially placed in there, we had to put that in there. Now the change in concentration will still look same. We got minus 1x because of the coefficient of 1 in front of hydrogen, minus 1x because of the coefficient of 1 in front of bromine, and plus 2x because of, well, we're adding 2 hydrogen bromides. Now at equilibrium, they're going to look like this, and of course our HBr, we had 2 expressions at equilibrium, so we had 8 plus 2x and 15.2. So we plug that in right here. 8 plus 2x is equal to 15.2. When we solve for x, we should get 3.6. So just using algebra, right? So all I did was bring 8 over here, so that's why I subtract and then divided both sides by 2. Then when we solve for our equilibrium concentrations, it looks like this, and we plug in our Kc and get a value of 11.9, which is very similar to the 12.1 I think we got in our last one, which is completely fine. Basically with rounding and stuff like that, you're going to be off a little bit, but we basically have the exact same number for the equilibrium constant, which is good. So the next few, of course, same thing, still working with equilibrium constants. Where this one right here, or our next one, this is kind of an old diploma question. I know it doesn't say diploma example, but where we have a graph where we have our reaction like this, and we have our graph at equilibrium concentration. So we can tell that the numbers here, obviously it's starting at 30 moles per liter, and now this one's down to, so this 23 is for right, and the oxygen right here, that 15 is for oxygen, so the concentration of oxygen at equilibrium, and our SO3. Right, so if you extrapolate over concentration, that's why that one's there. Same thing, extrapolate over. So you should be able to solve this right here, because it says at what time does equilibrium get reached and what is the value for Kc. So remember, equilibrium is when basically all the lines are flat. So really we can kind of see around that 15-second, 20-second mark is when the lines start flattening out. So at 15 to 20 seconds. And for the equilibrium constant, once again, I want you guys to pause the video and try it, but you should get So I want you to try this one out and see if you can get the equilibrium constant of 0.0126. If you don't get it, you can open up the notes and see how I did it there as well, but just remember, be careful of the coefficients in front. And of course, last but not least, we do have one here, or two, where the math is a little more tricky just because we're given the Kc, we're given the equilibrium constant for one of those right here. We'll notice that there's no ICE table given out and it's just mostly algebra. So I'll go over example 4, and then example 5 is just going to be similar. I'm going to let you guys kind of work through that one. But if you want to try this one on your own, please do, as it is, well, once again, a little more complicated. But anyway, let's look at the reaction and start off with the ICE table. So when we write out our reaction, it's going to look something like this. So we have our carbon monoxide reacting with water vapor to produce carbon dioxide and, of course, hydrogen gas. So, of course, as we go through, we will need to put in our initial, where we have 2 moles initially of each reactant is placed in a vessel, and the reaction container is 500 milliliters. So that means that the concentration for both reactants is 4.00. We have no information about our products. They're going to be at 0. Now there are changes in concentration. The coefficients in front of everything is 1. So our reactants are all down by x. Our products are all up by 1x. So at equilibrium, these are the concentrations. Now we will notice from here, all we're given is just the equilibrium constant for the reaction is 4.20. That is it. So we don't have anything about equilibrium concentrations, only the equilibrium constant. So what that means is that when we start evaluating, because we are going to have to try to solve for x some way or another. So when we fill out our equilibrium law, it's going to look something like this. And when we plug in our values, we get x, x. And this is equal to our equilibrium constant of 4.2. Now, what we're going to do, so I don't have enough space here, so I'm just going to go to a different page to kind of see this, but we are going to need to do some algebra. All right, so the algebra we're going to have to do is we have 4.20 is equal to, we can simplify the top into x squared, and we can also simplify the bottom into 4.00 minus x all squared, because we had the exact same thing. Now, algebraically, what we can do is, you can imagine trying to solve for this is going to be kind of difficult, but because we have x squared at the top and 4.00 minus x down at the bottom, what we can do is take the square root of both sides, square root of that, square root of all this. Now this is going to simplify into the square root of 4.20 is 2.04939 is equal to square root of x squared is x, square root of 4.00 minus x, 4.00 minus x. So you'll notice now we're actually going from something that looked like we might need the quadratic equation to solve. Now we don't need it because we no longer have a square value. So from here you should be able to rearrange and solve for x. So we have this down in the denominator that we need to get rid of, so we're going to have to multiply both sides by 4.00 minus x. So remember, from here, we're going to have to multiply 4.04934 times this, and then we're also going to have to multiply it by x. So then what we end up getting is 8. Oh, sorry, that should be in red. Just kind of match what we're doing here. So we get 8.19756 minus 2.04939x is equal to x, right? And of course, once we actually kind of rearrange and solve for this here, we should get, we're going to bring this over here, and this is going to turn into a positive, and we have that, so we get 8.19756 is equal to 3.04939x, and we divide both sides by 3.049, and we end up getting x is equal to 2.69. And that is perfect, because from our previous page we had at equilibrium, we had concentration of CO is equal to 4.00 minus x. So we go 4.00 minus 2.69, and we get the concentration of carbon monoxide of 1.31 moles per liter. Concentration of hydrogen at equilibrium is 4.00 minus x, so that's 4.00 minus 2.69, and we get 1.31 moles per liter. Concentration of carbon dioxide was equal to X, so that is equal to 2.69 moles per liter, and concentration of, that should be water, H2O, because hydrogen gas was a product, that is equal to X, now is also equal to 2.69 moles per liter. And that is how we use our equilibrium constant in a little bit of math to fool around and solve. So of course, with these here, this kind of step is kind of common in order to solve for some of these here. So just don't be surprised if you do see this again, which, spoiler, our last example 5, you're going to have to follow the exact same steps. All right, so for that one there, I definitely want you to try example 5 on your own. Just because it is one of the steps that you will need to do, and when you do it, you should get your X value to equal 0.864922, and the corresponding concentrations, HI is equal to 0.27 moles per liter, H2 is going to equal 0.86 moles per liter, and I2 is also going to equal 0.86 moles per liter. So please try this one until you actually get the answers that I have right here. And of course, if you don't get it, just kind of let me know and we can hammer out a Google Meet and actually go through all these right here. So that is it for our ICE tables. Of course, your book has your workbooks has lots of these here to practice, and please practice them. These here, they're only going to get easier the more you do them, and of course the ICE tables are going to really pay off when we get into our acid-base section towards the end of this unit. All right, so our last lesson is on Le Chatelier's principles, which we're going to go over next. So please try as much of these as possible, and I'll see you guys for the next one.